Hi there, it's Jason from Codemanship with another video diary entry. Before we begin, please like and subscribe and ring the bell for notifications if you're interested in new content. Okay, so I'm going to talk a little bit today about reliability in the sense of modular software, and also about the role of dependencies in producing software that is more reliable. Now, if we visualize a software system as a network of dependent modules, and I'm using the term module very loosely here, I could be talking about functions calling functions, or classes using classes, or microservices calling other microservices, but a network of modules. If we visualize that network like this, for example, we could analyze the dependencies in our network of modules, in our dependency graph there, to figure out who depends on who, and therefore who has the most things depending on them. And that might be a very useful thing to know. So we could do build a table like this, for example. Now, in a larger code base, you probably need to build a tool or buy a tool that can do this for you. For example, there's ndepend for .NET developers that can do this kind of analysis for you. But we want to know who depends on who, and we can see that module E has the most number of things depending on it. So we might conclude that module E is the most critical module in that particular network there, that we might choose to pay more attention to module E, but we'll come to that later. But this is probably a very naive, sort of one-dimensional way of looking at it. If we think in terms instead of critical paths, or the call stacks in particular usage scenarios. So let's say we have a call stack where A calls a function on the module B, and B calls a function on module C, and C calls a function on module D, like that, for example. If we analyze the software in those terms, we may want to think about which modules appear in the most call stacks, in the most critical paths. And then we might come to a different conclusion about which modules are the most important, the most critical ones. So if we take a look at our network graph again, we've got a critical path here that you can see there that goes to the module in the center. And there's another path there that also goes to the module in the center. And there's another path there that also goes to the module in the center. So that appears at the end of all of those critical paths. So although it only has one direct dependencies, it appears in 3 scenarios already. Let's keep going. What other critical path does it appear in? Well, it appears in that path, and it also appears in that path. In actual fact, it appears in all of the critical paths. And so we might conclude that, in fact, the module in the middle there is the most important one. It's the most critical one, because if that fails, if that's broken, the whole thing is broken, basically. So it brings the whole system down. So we might want to analyze our code to figure out which modules are on the most critical paths. Now, you can do this by analyzing code, and you can do this dynamically as well with running code. For example, you could run all of your customer tests, if you've got them, or all of your acceptance tests, and instrument the code to measure which parts of the code are being executed the most often or appear in the most critical parts. So there are lots of different ways of doing this. One way that I found quite helpful, though, to predict which modules appear in the most critical paths is to use the Google PageRank algorithm. So we could be talking about modules depending on modules in software, or we could be talking about web pages linking to web pages. The principle is the same. Which web pages have the highest rank in the system? So we could use the Google PageRank algorithm, it's an iterative algorithm, to figure out the rank of modules within the system. I'm not going to spend too long explaining the PageRank algorithm. You're very welcome to Google it. But we found that actually does work if you're analyzing dependencies in software as well, and identifying which parts of a network of dependencies are actually going to be the most critical. And it's a pretty good predictor of that. So if we were to run PageRank algorithm analysis over our network of dependent modules, we might end up with a very different picture, sort of a heat map, if you like, where the module in the center there is glowing red hot. Some modules are green, they're pretty cold. We don't need to worry too much about them. And so we can get a sort of a heat map, a sense of the terrain, if you like, in terms of which modules actually present the highest risk in terms of the fact that the impact, if they were broken or if they failed, would have the most ramifications within the system. So that's a better way of identifying through static analysis of the modules in your code. And you can write tools to do this, and you can buy tools like NDepend for .NET developers, for example, that can calculate the rank within the system. But it's a relatively straightforward thing to do, actually. So it's worth knowing. Of course, at the code level, that's relatively easy. At a sort of a service-oriented architecture level, a bit more complicated to figure out where all those arrows are pointing. But that's a job that I think that's a good job for an architect, actually. If you're a sort of an enterprise type architect, one of the valuable roles you can fulfill is presenting teams with this picture, the overall picture of this is how you fit in with the rest of the system in terms of risk, in terms of the rank within the overall system. So PageRank can be useful in sort of determining which parts of our code are what I call load bearing, in the sense that most things directly or indirectly depend upon them, and therefore the impact across the system if they fail would be the highest. So what do we do with this information? Well, that's the one glowing red hot there. Well, I've come up with a design principle. It's been around for quite a while now, which I call the Dependable Dependencies principle. And it really is about the direction in which the arrows are pointing in our software architecture. And the sort of the simplest version of it is that modules should depend on modules that are more dependable than they are. Basically, the more things depend on you, the better tested you need to be. But maybe a more useful way of expressing that would be to say that a module's rank in the system, the higher that is, the lower probability it has bugs should be, the less likely it should be to fail or to be broken. Now that opens a whole can of worms about, we've identified which code is the most critical in terms of dependencies. There are, of course, other factors in the criticality of code. But in terms of dependencies, we've identified where that load-bearing code is. We've got our little heat map there. But what are we going to do about it? And that's where we need to think. We need to analyze that code and understand and ask some very important questions. How likely it is that this code will be broken, basically. How likely is it to have bugs? And there are a number of factors in that. One that is a very good predictor of bugs is complexity. Basically, the more moving parts a machine has, the more likely it is to break down if we tinker with it. So complexity is a very good predictor. Another really good predictor is how often that code is changing. The more often, basically, the more we change it, the more likely it is that we'll break it. So we could take those two factors into account, and both are relatively easy to measure. If you're using GitHub, for example, you can pull GitHub statistics, do analysis to figure out which code is changing the most. And you can use code analysis to figure out how complicated that code is in various dimensions. And then there's a third factor, which is very, very important. Code may be complicated, but it may be really, really well tested. So the third factor is test assurance. Now, I'm deliberately using the word assurance and not coverage. Test assurance, I think, is a more meaningful measure. It asks the question, if this code was broken, how soon would we know? It's a very important question. If we broke this code, how soon would we know? So coverage is a factor in that: line coverage, branch coverage, conditional coverage, but also how often we're running those tests, how often that code is being tested. So we need to understand when code changes, how soon was it retested? And that's why it's very important to have tests that run fast. So the more often we test it, the less likely it is to be broken. So we can bring all of those factors together to predict where in our code or where in our system we're most likely to have problems, we're most likely to break it, basically, and therefore where we should devote more effort to testing and quality assurance. And I'm not just talking about unit testing or integration testing or system testing, that kind of stuff. I'm also talking about good old-fashioned techniques like inspections. Don't underestimate inspections. They're still a very effective way of spotting bugs that we didn't spot. So get together with your team or with a pairing partner and go through that critical code line by line. With every line of code, ask, is it doing what it's supposed to be doing? And also ask yourself, when might it not work? Are there any preconditions for this particular part of the code that need to be observed? And can those preconditions ever be broken? So step back up through the call stack going, can that number ever be zero, for example? Are we going to end up dividing by zero one day? Or does the system not allow that? So don't underestimate those old-fashioned techniques. But certainly when it comes to targeting testing and test automation, I found this a very useful technique to identify, usually typically in the average business system or the average commercial product. So we're not talking safety critical here, just your average commercial software system. 5 to 10% of the code is what we call load bearing. It would be a big deal if it failed. Now, going beyond that, there are other factors, and I can talk about that in later videos. So when we were talking about critical paths, those call stacks for particular features or particular user actions or whatever, particular test cases, basically, there are other factors in how critical a path may be, and therefore how critical the code on that path might be. So you might have a feature that's only executed once a year, but maybe it's a really, really big deal if that feature doesn't work, if it fails for any reason. So you need to be super, super careful when you're writing and changing that code. So you can build that, you can incorporate that into your process as well. It is very useful to have an understanding of which features and which scenarios, so customer tests, for example, are the most critical, the most important, or will have the biggest impact if they fail. And to maybe factor that into your calculations as to which code, therefore, needs the most attention when it comes to testing and inspections and that kind of activity. Okay, so there you go. That's the dependable dependencies principle. I hope this has given you some food for thought. We'll talk in a later video about how test-driven development can help us to achieve the goals of the dependable dependencies principle. But we'll also talk maybe about some of the other techniques that you might choose to use that take you beyond the levels of reliability you can achieve with TDD, usually. So, hope you've enjoyed that. Until the next video, you take care.